In this lecture, I'll provide an overview of basic statistics. In order to test our hypotheses, we must understand our data. The appropriate data analysis strategy is based on the types of variables we have. But let's start with a more basic question. What are variables? Then I'll describe descriptive and inferential statistics, including how to determine the appropriate test for a study. So what are variables? The word variable comes from the Latin word variare, to vary. A variable is a characteristic of a study participant that is different for each case. This is distinguished from a constant, a characteristic that does not change across individuals within the population or sample. We look for relationships between variables. If something is constant, there is no difference and no way to describe that difference. This is what makes psychology so interesting. We have differences and we can go searching for reasons why they exist or what effect the differences have on us. This is also what makes statistics a different way of thinking than math. In math, you have concrete numbers to deal with. In statistics, you have distributions of likelihood. You have to be okay with confidence intervals rather than a concrete answer. The type of data we have is really the key to knowing the appropriate statistical test. It really has little to do with whether the study design is experimental or correlational. Categorical data is data represented by categories or nominal groups. This could be things like male and female, major in school such as psychology, biology, engineering, etc. Ordinal data is in a rank order. So you can think about rank order of a high school class. Interval data is on a scale of even units of measurement, but there is no absolute zero. So for example, temperature in Fahrenheit is on an interval scale. 0 degrees Fahrenheit is relative. A ratio scale has even units, but it also has an absolute zero. So something like height. There can be 0 height. So in general, experimental groups are going to be categorical. You have an experimental condition and a control group. Or you may have 2 experimental conditions or more and a control group. Many outcomes or dependent variables will be measured on an interval or ratio scale. Questionnaire scales are often treated as interval scales. Some would argue that the units are not always evenly interpreted, like on a scale of 1 to 5. But for ease of statistics, they are treated as such. Ordinal scales are not commonly used and require a different statistical strategy, and I'm not going to go into that in this presentation. We need to first talk about the 2 types of statistics that we deal with in talking about research. The first are descriptive statistics. These are statistics used to summarize and describe the research sample. The second are inferential statistics, which are used to make inferences from the sample to the population. To explain this in pictorial form, we start with a population. the lighter color gold oval we have here. Perhaps this is all UAB students, and we want to know something about the population, say SAT scores. The value of this in the population is what we call a parameter. It is something concrete. There is a number for the average SAT scores for all undergraduate students who are enrolled in fall 2017. If we don't want to contact all students, we will want to take a sample, and then we'll generalize to the larger population. So we take a sample. We can take samples from different portions of the population. This is where sampling comes into play. Our sample may or may not be representative of the full population. Once we have a sample and we take measures of the sample, we can describe the sample using our descriptive statistics. If we take samples using random sampling, we'll get a better estimate than just getting a sample from one place, say the psychology department. Once we have our sample descriptives, we try to generalize or infer about the population, about the parameters of the larger population. So if our descriptive statistics has a mean score of 1376, we will try to infer to the larger population. However, it's not always going to match. In fact, it rarely will. When our sample descriptive statistics do not match the population parameters, we call this sampling error. So what kind of descriptive statistics do we have? We can describe a sample by talking about the central tendency of the data, using such things as the mean, median, and mode. We can talk about the spread or variability of data, which includes the variance and standard deviation. And we can also talk about the skewness, which is the extent to which it is symmetrical around a central point. So let's look at central tendencies. The mean is the average. The median is the central value, or the 50th percentile. The mode is the most common value. In a normal distribution, like that displayed here, all of these are the same. We generally hope for a normal distribution, as many of our inferential statistics use the assumption that that's what we're dealing with. The spread or variability is how steep this curve is. A distribution with a greater variability will be more flat. One with a small variance will be steeper. So most of the data points will lie in the center. When we talk about skewness, we are talking about the symmetry around a central point. We also hope for a distribution that is not skewed. A positive skew is one in which the scores or observations are bunched at the bottom of the range, so that is to the left. A negative skew is one in which the scores or observations are bunched at the top of the range, to the right. These often seem backwards to people, these labels. So a good way to think about it is to use the mantra, "The tail tells the tale." It is the tail, or the long end of the distribution, that gives its label of negative or positive. So these descriptive statistics, the central tendency, the skewness, and the variance, together describe our sample data. From there, we use inferential statistics to generalize to the larger population and to test the probability that variables are related to each other. Inferential statistics compares a hypothesis to an alternative statement. To describe this, I will use the example of having two groups we are comparing and want to know if they are different. We use statistical significance to tell us the chance that the observed difference between our two groups is by chance. If two groups were the same, in reality, what's the chance you would get the result that you got? Statistical power is related. It is the likelihood of finding a statistically significant difference when a true difference exists. Sample size has an impact on both statistical significance and power. The smaller the sample size, the lower the power to detect a difference. This is because the greater sample size, the better the estimate of the population parameters, and the lower the sampling error. So let's look at an example. If the red distribution here represents an experimental group, and the blue distribution represents a second group, so group 2, we can see that there is an observed difference in the means. One lies at 0 and the other lies at 1. However, the question becomes whether it is enough of a difference to be considered statistically significant, which is often defined as having a 95% confidence rate that they are different. In this case, the answer would be no. To know this, however, you would have to figure what's called a t-statistic and look it up on a probability table. So some basic statistics that we use are a t-statistic, which is testing the means of two groups, like I just showed you. An ANOVA, which is testing the means of two or more groups. A correlation, which tests the relationship between two continuous variables. And regression, which tests the relationship between two or more continuous variables. And continuous variables can be either interval or ratio scales. You may or may not notice here that the top two tests include the means of groups, which generally means you are dealing with a categorical variable. Otherwise, you had a continuous variable that for some reason you turned into a categorical variable, which does happen sometimes. The bottom two tests have predictors that are continuous, either interval or ratio scales. So let's talk about correlation and regression. Correlation uses an R statistic. It has a range from -1 to +1, with a 0 meaning that there's no correlation. This represents the degree of relationship between two variables. We use a scatter plot to plot the relationship between these variables. If you look at the center scatter plot, it does not look like there's a pattern. We tried to look for a best fit line. We are able to do that once we move to a stronger relationship. And once you get to a very high relationship, like point A, 0.8 or 1, it's very easy to see that relationship. So when we're looking at these correlations, a positive number, such as 0.8 or 0.3, means that as you go higher on one variable, the other variable also goes up. A negative relationship has a line that goes in the opposite direction, such that as you go higher on one variable, you go lower on the other. I'm going to say it again, even though you've probably heard it many, many times. We need to remember with this that a correlation does not mean there is causation. And I want to talk a bit about linear and nonlinear relationships. A correlation, like I said, looks for a best fit line. When you have a linear relationship, that works. Not all relationships are linear, however. This here is an example of a nonlinear relationship. We have average stimulation on the x-axis. As stimulation goes up, we at first have an increase in performance. And if you just looked at this portion of the scatter plot, it would look like there's a positive correlation. A low level of stimulation may be sleeping. So you can imagine people need some level of stimulation to have better performance. However, there seems to be a midpoint at which performance hits its peak and then drops down with increasing stimulation. This curvilinear relationship will not show up by conducting a typical correlational analysis. It will look like there is a zero correlation. So one of the things we need to do is plot out the data to be able to see that this is here. And then we have other alternative statistical tests to do to find this type of relationship and look for the significant value. Now, regression is similar to correlation, but it allows for more variables. You can have multiple predictors predicting one or more outcome variables. So if you like analogies, it is to a correlation as ANOVA is to the t-test. Regression is finding the best fit line for the variables of interest and predicting the outcome variable. Because of this, we represent regression with an equation of a line, using a variable to represent each of our predictors and y as the outcome. So here we have predictor 1 represented as x1, predictor 2 as x2, and predictor 3 as x3. For all of these inferential tests, we want to take our data and assess the extent to which our test results could have been achieved by chance if there really was no relationship, the null hypothesis. We're also looking at this from the standpoint of using our measured variables and relationship between them to assess the constructs and their underlying relationship that we are really interested in. So here, our constructs that we're interested in are motivation and school performance. But we can't test these directly because these are constructs, they're abstract. We need to turn them into our operational definitions. So in this case, we have intrinsic motivation on the DC scale. This is related, or we test to see if this is related, to percentage correct on tests in school. We then make inferences about what we find on our measured variables to try to understand the underlying relationship. Here is a more specific table of tests with details of types of t-tests and ANOVAs. Always remember, however, that knowing the appropriate test does not tell you if the design of the study was experimental or not, meaning that you cannot tell from the statistical test whether you're testing a causal relationship. We have to know the study design to know whether we can come to any causal conclusions. So, if we want a strong causal inference, we need to do experimental research. We need to create an experimental design in which we manipulate our variable of interest or multiple independent variables, and we control the environment by randomly assigning people to conditions. We can do studies that have a weak causal inference, but may be more externally valid in that they are more applicable and generalizable to the outer world. These are our quasi-experimental designs. Although we are able to manipulate our independent variables, we're not able to control everything, and we often are not able to randomly assign people to conditions. And then we have our correlational research, which measures variables as they naturally occur. But we always remember that there is no causal inference that we can attain from these tests, from this design. I hope this has been a useful review of statistics for you, and you may have learned a little bit more than you knew before if you haven't yet taken research methods in statistics.